Hello everyone. So we are at lecture number 3, and in this lecture we will talk about Taylor series in 2D and 3D. So suppose I have a point x1 which is x plus delta x. I have a point y1 which is y plus delta y, and I have point z1 which is z plus delta z. So suppose if I want to write down the Taylor series expansion in 2D, then I want to know the function value at x1 comma y1, that is function value at x plus delta x comma y plus delta y. It will be given as function value at x comma y plus partial derivative of that function with respect to x at point x comma y delta x plus partial derivative of that function with respect to y at point x comma y delta y. Then I will have 1 upon factorial 2 times partial derivative of this function with respect to x at point xy delta x square plus 2 times partial derivative of this function with respect to y at point xy delta y square plus 2 times partial derivative of this function with respect to x and then y at point xy delta x delta y, and so on and so forth. So this will go till infinity. So this way we can write out the Taylor series expansion in 2D. Now let me give you the expression in 3D. So in 3D, as I have already indicated that x is equal to x1 is my x plus delta x, comma y1 is my y plus delta y, comma z1 is my z plus delta z. I want to know the function value at x1, comma y1, comma z1, that is f of x plus delta x, comma y plus delta y, comma z plus delta z. So this will be f of x plus delta x, y plus delta y, comma z plus delta z is f of x, comma y, comma z plus partial derivative of this function with respect to x at point x y z delta x plus partial derivative of this function with respect to y at x y z delta y plus partial derivative of this function with respect to z at x y z delta z. Then the next term will be 1 upon factorial 2 partial derivative of this function with respect to x, that will be 2 times partial derivative at point x y z delta x square plus 2 times partial derivative of this function. This 2 times mean I am taking the partial derivative 2 times with respect to y at point x y z delta y square plus 2 times partial derivative of this function with respect to z at point x y z delta z square plus 2 multiplied by partial derivative of this function first with respect to x and then y at point x comma y comma z delta x delta y plus 2 multiplied by 2 times partial derivative of this function with respect to first y and then z at point x y z delta y delta z plus 2 multiplied partial derivative of this function with respect to first x and then z x comma y comma z delta x delta z. So this whole thing is basically coming in multiplication to this 1 upon factorial 2. Then this series will go till infinity. So this way we can write down this Taylor series expansion in 2D. Now I want to give you one important note about polynomial function. So as we have indicated that Taylor series is basically f of x naught plus f prime x naught x minus x naught plus that 1 upon factorial n f to the power the nth derivative of function f at x naught x minus x naught to the power n. Then those terms which are coming after this will be called Rn. That is the error. Rn is my truncation error. What is the order of Rn? The order of Rn is x minus x naught to the power n plus 1 upon factorial n plus 1, n plus 1th derivative of this function at point x naught. So suppose my polynomial is of first order. Suppose I have a function f of x that is of first order polynomial, and that is x. Now since it has order of the order of this polynomial is 1, so if I take the let's do one thing. X naught is equal to 0. Zeroth order approximation if I do, then it will be f of x is equal to f of x naught, that is 0. If I take the first order approximation, that will be f of x 0 plus f prime x 0 x minus x 0, that will be x. So for first order polynomial, if I do the first order approximation, my error is 0. So what I want to say is that for a polynomial function of nth order, if I take the nth order Taylor series approximation, then error will be 0. So suppose I take one more example. My function f of x is x square plus 2x plus 1. The first order derivative is f of x is equal to 2x plus 2. The second order derivative is 2. Now I take the second order approximation for this function. That will be f of x is equal to f of x0. My x0 is 1, x0 is 0 plus f prime x0 x minus 0 plus f double prime x0 x minus x0 to the power 2 upon factorial 2. That is f of x is equal to, what is f of 0? F of 0 is 1 plus f prime 0 is 2 x minus 0 plus 1 upon 2. F double prime 0 is 2 x minus 0 to the power 2. Then f of x is equal to, this 2 and 2 will cancel out and it will become x square plus 2x plus 1. So as we can see that we are getting this function. So for a polynomial function, if I do nth order Taylor series approximation, then that approximation will exactly be similar to that function. So that is what I wanted to say about polynomial function. In the next video lecture, we will talk about the applications of Taylor series, which is going to be really important. So we will start with linearization, then we will see how Taylor series is applied in root finding, how Taylor series is applied in finding the finite difference form of of derivatives, first derivative and second derivative. Then we will know how Taylor series is applied in finding regression, linear regression and non-linear regression. So these topics are going to be very interesting, and we will talk these topics in the subsequent videos. So thank you so much for listening, and I'll see you guys in the next video. Thank you.